You have probably heard it said that what starts here changes the world. And today is about changing the world, that part of it, the second part. And it is our honor and pleasure to have with us today Dr. MIT Professor Dr. Robert Langer. We hope he's been here before, and we hope he comes again, but he's here today, and we're delighted. My name is Bob Metcalf, and I'm Faculty Director of the Innovation Center in the Cockrell School of Engineering, where it is our job to encourage faculty and students to start companies, to change the world, to have impact through startups. Now, Dr. Langer, who just recently won the Queen Elizabeth Prize, is a member of all three academies. He can talk about anything for hours on end, but what we're asking him to talk about today is two things. One is, how can you remain a world-class research professor and still have time and energy to start companies to have impact with your innovations? And that'll be in the first session. And then the second session, we're building a new medical school. What advice does Dr. Langer have for us in how to build that medical school so that it's innovative and has impact? In the first section, Professor Nicholas Pepys, who's the head of biomedical engineering, will join us and interviewing Bob. And in the second session, Clay Johnston, Dean of the Dell Medical School, will be here to get that advice.
Good afternoon. Thank you all for coming. Bob, thank you. It's really a great pleasure to see you here. I know you woke up at 3:30 in the morning in Madison, Wisconsin to make it here. I'm delighted you are with us. I want to give a small introduction before we go into pursuing innovation. Bob Langer is like all of us, a classical example of American ingenuity. He was born on August 31st, 1948, in Albany, New York, comes from a family that had a father who was a small businessman. In fact, he was a liquor store owner, and a mother who was staying at home taking care of two kids, Bob as his youngest sister. He got very excited because when he was in primary school, his grandfather was playing mathematical games with him. And then in high school, or junior high, he started getting these Gilbert sets, if some of the old-timers remember them. One on chemistry, he loved it, and he was at home playing with it. He decided to go to chemistry. He went to Cornell University in 1966. And while he was a graduate of the Mills High School that some of you know in Albany. Then after that, he went there, and while he was there the first semester, he loved chemistry, but he decided to pursue chemical engineering, Cornell. There was a professor by the name of Bob Finn that was a biochemical engineer that really helped him in that decision. After he finished, he moved to MIT. He started working mostly in the biochemical field. He finished MIT. We were classmates, of course, at MIT, working in the same floor, proximate laboratories. And there was the big decision. He had many, many, many offers from oil companies. He was a chemical engineer. He still is. He decided to do something different. In 1974, he decided to join a medical group. Professor Judah Folkman at Harvard. He was a young man at that time. He was collecting unusual engineers and individuals like Bob. And he went to that laboratory, and the rest is history. He started working on angiogenesis with Judah Folkman. That's where he met people that have become other legends in the field, like David Kessler, who became an FDA commissioner, like Henry Brem, that probably he will mention in his work, and of course Jay Vacanti, with whom he started the tissue engineering. He started at MIT in 1977, first as a visiting professor, and then in 1978 as a regular assistant professor. Not in biomedical engineering, not in chemical engineering, but in nutrition and food science. Why? Because in those days it was difficult for chemical engineers and even biomedical engineers to accept the idea that an engineer would be working on problems related to the biological field. And he has many stories to tell you about it. In those very early days, he came up with the first patent. It was a patent that it was a technology with which he was trying to release, to deliver macromolecules from polymers. And all of you who have heard polymers, you know how difficult that is. Well, Bob was able to do it in an ingenious way. It took him 7 years to have the patent issued. The patent was issued in 1993. And eventually, after a lot of efforts that he may decide to tell us about, it ended up going to the company Alkermes, and it became the Prolise technology. It was one of the first technologies, and then followed many other technologies. In 1989, he became professor of chemical engineering. He's now the institute professor at MIT. There are only 12 institute professors. Bob has really been a tremendous innovator, an entrepreneur, yet at the same time a fundamental scientist. He continues doing fundamental work in a number of subjects, while at the same time carrying out really all the more entrepreneurial activities that he has. He is a tremendous inventor. For those of you who don't know it, he has 1,100 US patents. If you add the international ones, probably many more. He has about 1,300 publications in refereed journals, about 100 of them in Science and Nature, and I don't know, maybe about 40 in the Proceedings of National Academy of Engineering. For those of you who count H indexes, 209, and citations about 167,000 last night. By far, by far the most cited, and actually Google Scholar has forgotten his most cited paper, the paper with Vacanti in Science, which is about 9,000 citations. For some reason, it's not mentioned. So add another 9,000 there. He has been recognized everywhere in the world. I don't want to embarrass him too much, but some of us have honorary doctorates. Bob has 24 honorary doctorates from Harvard, Yale, Louvain, ETH, everywhere in the world. Bob has received many, many awards, not only from the chemical engineering and the biomedical engineering and the control release community, but more importantly, he has received the Wolf Prize from Israel. He has received the Millennium Award, which is the equivalent of the Nobel Prize from Technology. It was given in Finland. He has received several other major awards from the American Chemical Society, like the Perkinel Medal, the John Fridge Medal. Some of these awards have been received before by luminaries like Guglielmo Marconi and Thomas Alva Edison and so on, and that puts him in the same list to understand really where he is. From the United States, he has received both the National Medal of Sciences and the Medal of Technology and Innovation from two different presidents, President Bush and President Obama. The latest recognition, the Kyoto Prize from Japan last year. The latest recognition, he will get it in October, is the Queen Elizabeth Engineering Prize. I know he doesn't like me to talk about money. It's £1 million. Last year, he received in Hollywood the Breakthrough Prize, $3 million. These are prizes. These are not awards for research. From Michael Hall, believe it or not, in a very, very interesting, I guess what I'm trying to say, this is a man who saves people. This is a man who comes up with new ideas in solving problems, who helps people with his companies, and he is a great entrepreneur. Before I finish my introduction, I'd like to tell you the companies that he has started. Accusphere, AIR, which is advanced inhalation technology research, Arsenal, Bind Therapeutics, Blend Therapeutics, Ecotherapeutics, Enzatec, which is part of Alkermes now, Gecko Biomedical, In Vivo Therapeutics, Kayla, Microchips, Momenta, Pixar Bio, Pervasis, Volmatrix, Selecta Biosciences, Semprus Biosciences, Seventh Sense, SQZ Biotech, Teris, Transform, T2, and two that I left last. Moderna Therapeutics, that all those of you who follow it at this moment is standing on $900 million funds that they have raised for the research. I've never heard any company which is not public having that much money for research. And the last one is one that is dear to our heart of all of us, Living Proof. If you don't know, Living Proof is the company that Jennifer Aniston is advertising with the hair. And there are some nice videos where you can see Bob and Jennifer Aniston together.
I'm a trustee of MIT. At the beginning of every trustees meeting, we hold a prayer. And we thank God that we do not have a medical school. But Boston has lots of medical schools, and Austin is about, I guess, has a medical school now.
Well, we're not accredited, so we can't really say that we can teach students yet. So we don't quite have a medical school.
And this is the dean, Clay Johnston of the Dell Medical School. And the theory of this session is that we're going to ask Bob Langer for advice on how to design our medical school. That's a little presumptuous of me to say, but I'm going to give you advice on how to design your medical school. Yeah. No. Is that all right with you? We proceed
of course.
On that? Is that okay with you?
Again, I'm not sure how much my advice is worth on this, but I'll be happy to try.
Well, it's got to. Your advice should involve engineers and entrepreneurs, I think.
I can do that part.
Okay, good.
Yeah. Good. Yeah.
You have a question?
Great. Wonderful to hear your comments before. I mean, it's just great to have you here, and on this now very special day, the Langer Day. And
yeah, I'm hoping that they're going to let students out of school for it.
I know, yeah. Yeah, better than a snow day, right? Because usually the weather's a lot nicer than this. And I mean, first thing I think we ought to recognize is that you are exceptional. And you're not just exceptional, you're exceptionally exceptional. And I'm not just saying that
I want my wife to hear this.
Well, I'm not saying in all respects. Yeah.
No, that's okay.
Yeah, because my wife certainly doesn't think I'm exceptional either, so they definitely are the worst critics.
But my wife thinks that you're exceptional.
Yeah. But the reason I say that isn't to flatter you, because you certainly need no further flattering after Nicholas's wonderful opening, and also after all that you've done. But it's to say that your experiences may not reflect the average experience for an investigator working in a fabulous university, right? And so I want to start with that because I think it's important, because the reality is you didn't have a mentor, as you told us. You didn't really have somebody who was working in the same sorts of spaces that you were previously. I mean, every other area, it's sort of agreed that if you don't have a mentor in that sort of leadership, you're not going to be successful in an area. And yet that was not the case for you. You weren't working in a medical community. I mean, it's a gigantic medical community, but MIT itself, it's not that it just doesn't have a medical school. Over time, I guess now, biomedicine is so big at MIT. But particularly when you started, it wasn't so big at MIT, and that wasn't necessary for you. You did it by yourself, in essence. I mean, obviously, you're pulling in all sorts of people, but you had unbelievable successes, one after the next, as an individual. So exceptionally exceptional doesn't mean that we're going to necessarily be able to have 1,000 of you out there just by saying, hey, it's possible, right? So that gets to the point of, if we just looked at you, then I think we could just say, we don't need a medical school. Medical school is just a distraction. And Bob, I think your sentiment, medical schools cost a lot of money, and they are distracting to universities. So my first question to you is, do we need a medical school?
Well, let me try to answer it this way. I do think medical schools, I mean, I'm very glad, and I mean, Bob didn't talk about this that much, but I'm certainly very glad from my standpoint at MIT, you know, that Harvard Medical School is 10 minutes away, and that those great hospitals in Boston, like Mass General and Brigham and Women's and others, Children's Hospital, are also very, very close. I think that at multiple levels, I feel that that's been helpful to my career. When I was a postdoc, as I mentioned, I worked at Children's Hospital in the surgery department, and I think that stretched me. And I do feel that that kind of stretching was very helpful to me. And then separately, now as a faculty member, like I probably have 8 people in my lab who are, you know, really fellows, you know, clinicians who, you know, in other words, that's like fellows are after, for people that don't know, that might be after residency, and they might do 1 year of clinical work and 2 years of research, and they could do the research anywhere they want. And I think having those people, and they're of all different disciplines, like gastroenterology, ophthalmology, dermatology, surgery, neurosurgery, I think having those people in our lab is wonderful for me and for all the students. And the way I kind of think about it is like this, and this is oversimplification, but I've used this, said this before, and I think it's partly right. So I think when you get a PhD teaches you how to rigorously find good answers. You know, I think that that's what you do. You take a problem, you do a PhD thesis, 4 years, whatever, and you really learn how to find good answers. But one of the things that really disturbed me, I guess, when I was a young chemical engineer, is I didn't think that the questions that which is different than the answers, I didn't think the questions that the chemical engineers were asking were very good in the medical area. And what I feel is that the MDs, and I feel this is very true for our lab, the MDs know how to ask good questions. And so I really feel that by bringing them into the lab, they help me, they expose us to all these medical problems, they expose the graduate students to medical problems. So I'm thrilled that we have the Harvard hospitals, you know, in a way having people come to our lab, and some of those people have become superstars clinically, academically. I've had this fellow, Omid Farrakadazad, who's now at Harvard. He started as a fellow with me. He's actually started 3 companies. And he's raised hundreds of millions of dollars, but he's, you know, sort of pioneered the whole idea of nanotechnology into medicine. But I'm just so glad that we do have Harvard Medical School and we do have these hospitals, because it enables us to do things that I don't think we'd ever come close to doing otherwise.
Yeah, so they're working in your lab. You've got MD, MD-PhD students and others and fellowship working in the lab.
Yeah, and they work together, you know, and I think it's really enables them to do things and to do projects that...
alongside engineers.
Exactly. I'll even just give you a recent example, which I think is a great example of this kind of thing. So I've had, so Bert Vogelstein is a very famous molecular biologist, clinician. He's at Johns Hopkins. And so there was a guy, Gio Traverso, and he got his PhD with Bert, got an MD, and he's a gastroenterologist. But came up, and now he's at Mass General, and he was a fellow. And, you know, he was attracted to the kind of things that we were doing, which is in bioengineering. And a couple of years ago, Bill Gates came to see me and was interested in, you know, what new ways of treating malaria, because he said, well, people, you know, when they don't take pills, you know, and people don't come back for a second pill. You know, could you come up with a pill that might last for a week? So I had certain polymer ideas that I thought might enable you to make super, super long-acting pills. And so they gave us quite a bit of funding, and Gio heads that project, but we've got some superb new polymer chemists helping on it. We've got you know, a bunch of bioengineers, and they're all working together to create, you know, these super long-acting pills. And so I feel like having that kind of team effort is, you know, and you certainly, you know, want to make sure when you design pills that are unlike anything people have ever seen before, that you've got a great gastroenterologist and that you have people thinking about these things.
Well, let's go to that. So before you were talking about that, you know, projects should proceed from a good paper. You know, you should be working on the science. It should be really interesting, important science, and then that can lead to something potentially translatable that might yield a company. But you actually have given now 2 examples of things that have started with a practical need that you're addressing. Actually, three, if the two hair products,
Right.
and in this example. So how do you, where do your questions come from? Is it a variety? Is it a spectrum? Or are you always looking for practical consequences of your next paper?
Yeah. Oh, that's a great question. And we actually go both ways. You know, I think sometimes they're driven by specific problems, and sometimes they're just driven by broad issues. Even if I took the one that we just mentioned, the gastrointestinal one, or even the hair ones, the way those started, or I should say significant elements of them, were sort of just basic ideas. Like, so I had these ideas on shape memory polymers. What I mean by shape memory polymers, it might start out in one shape, but then you could have a stimulus like a pH change or a temperature change and have it, you know, change shape in a major way. So we published one of those in Science and one of those in Nature in the 2002 and 2005. But when Bill Gates mentioned to me about this thing, I actually had this idea, since we'd done these other more basic things, that we could apply those shape memory polymers to these pills.
But when you were, so that your idea though about shape changing polymers,
Right.
It already is practical, right? As soon as you say that, oh, I know exactly what he's doing. He's thinking about, okay, pH sensitive drug delivery vehicle. And so that was probably in your head even then as the potential practical consequences of that science.
Not that, actually. I had some other ideas which haven't,
Well, maybe not that specific.
Yeah, but in a way,
indication.
but I mean, you're raising a good point. So you might make a distinction between like an engineering kind of discovery, which is a new class of shape memory materials, or even a chemistry discovery like the hair products. That was an idea of creating these libraries which we felt would be useful for a variety of things, and weren't sure what. And that's how I was going to answer that. But I think that in contrast to sort of a fundamental biological mechanism.
Right.
I mean, so I would say that there's a spectrum of research. You know, in other words, we're not trying to figure out a new gene structure or something like that, but we are doing work that is fundamental in the sense of leading to new materials and without necessarily a clear application. Also, I guess I'd say that probably if I look back at some of the applications I might have had in my mind on a lot of these, they wouldn't have turned out to be right.
Right. But I guess part of your secret sauce is that you're thinking about your discoveries as being platforms.
Yes.
Right? So already you're to a point where you're saying, I don't know the specific application, but I suspect that this platform will yield specific applications that could be valuable. True?
I always hope so.
You always hope so.
And in other words, I came up with, you come up with these things that you feel don't exist, and if they did exist, but that's part of the engineering thing, right?
Right.
That you create, so you come up with ideas of things that don't exist, but now that they do exist, then it will create opportunities. And of course, when originally I did this, my thought was, other people will come along and figure out how to use it for this or that.
But those two characteristics are not necessarily what goes into a Science or Nature paper.
Well, actually, it's interesting. So classically, that would be true. But I'd say, the kinds of things that get in Science or Nature for bioengineering and chemistry, I think it does now. In other words, we've been doing it since, like what Nick said, the first paper we wrote was a biology one on the discovery of the first angiogenesis inhibitor. That was 1976. The first one in Nature was this idea of controlled release of large molecules, which hasn't been done before, and that was also in 1976. And what those do is they fit the criteria that I was mentioning in the sense that they created sort of platforms in a way, but probably if I look back at what I thought that Nature paper would be useful for, I would have been wrong. I thought it was going to be useful for insulin or other things I didn't really know.
Yeah.
But I think when I started doing that, and then we just kept doing it, so most of the things that we've published in Science or Nature, at least for me as an engineer, they're not the classic biology Nature papers, but Nature and Science, I feel, felt they were transformative enough that they took them.
Oh, yeah. Even just the way you said that would be useful for. So that for you is an important criterion.
That I hope it will, yeah.
Yeah.
That I hope it will.
So not necessarily true if you're primarily interested in just the discovery. You know, I'm curious.
Yes.
I want to figure this out. This is going to be something cool. I mean, the two definitely are related, right?
Yes.
All knowledge as we move it forward. We hope that it'll someday be useful. But for
Yes.
you, it's tied to the areas that you're drawn into.
Yes, and I think that that's part of me being, like I said, that's part of the engineering.
That's your.
But I think what you're saying is correct. I mean, we're not doing, in our lab, we're generally not doing fundamental biology as an example.
Yeah. So I just wanted to bring that out there because I think it's important to think about that as sort of part of your phenotype. It might not be present in all the phenotypes that are represented in a broad university.
Oh, I think you're right.
And so that gets back to, well, let's go back to how you construct your lab.
Okay.
So then how do you said the MDs are good because they help you they ask good questions.
Yes.
Do they ask you the questions that lead you to develop the platforms, or do they ask you the questions that lead you to find the applications, the practical applications for your platforms, or do they ask you the questions that tell you whether those applications will actually be feasible if moved forward?
I would actually say all three. Mm-hmm. You know, I think, and which is partly why, to me, it's so valuable that they're there, you know, and that we have this interaction with them. I would say actually all three.
Yeah.
You know, I can think of examples of all three.
Yeah.
So your lab is in the Koch Center for Integrative Cancer Research.
Yes.
And it's, as I recall, 24 labs, 12 biologists and 12 engineers.
Yes.
A big experiment in the conduct of research. How's that working out?
Yeah, well, I think people think it's working out very, very well, but I'll go over that a little bit more. So what MIT did, you know, classically, and I'm sure this is true here, it's probably true most places, and it's certainly been true at MIT. Classically, you know, if you look at a building, you know, there's going to be a building for, I'll make this up, the chemistry department, a building for the English department, a building for the electrical engineering department. So there are all these silos where there are these buildings. What we did is something very different. So our building has 7 different engineering disciplines, 7 different engineering professors, like chemical engineering, material science, bioengineering, you know, so forth, and then 12 kind of more fundamental biologists. There's also some clinicians too, but so that's an experiment, and the idea was that there would be what we'd call convergence. In fact, Nick has been involved in some panels on convergence. Phil Sharp, who's one of my colleagues, and we wrote an article in Science on this a few years ago, and it's I think, something that enables people, you know, the products of different disciplines of people working together. And it's, of course, it's not just the professors. I mean, part of the hope, and I think this happens, is that students meet other students, postdocs meet other postdocs, and so forth. So you know, it's an early experiment. Probably the building is 4 years old, but I think some criteria that could be used, depending on how you look at it. I'll give you an academic criteria and a business criteria. But the business criteria, there's probably been about 12 companies that have started and a number of products and clinical trials. And some of them, founders of the companies, for example, T2 Biosystems is a nanotechnology company that I started with Michael Seema, who's an engineer, and Tyler Jacks, who's actually the director of the building, who's a fundamental cancer biologist. It's done extremely well. They already have it's ultra-rapid diagnostics using nanotechnology, and they already got a product approved by the FDA, which I think is an incredible medical thing because it's basically new diagnostics for candidiasis, which normally take 5 days to treat, 5 days to diagnose, and now you can diagnose it in 2 hours, and that should save a lot of lives. And from a business standpoint, it's done well too. I think the market capitalization is about $350, $400 million, and they didn't raise that much. From an academic standpoint, I mean, which I think we're all proud of, you know, it's a cancer center in addition to being this building, and the NCI reviews cancer centers all over the country. And this October, they did a site visit on us, and, you know, there's like 20 site visitors, and every single person gave the score of 1.0, which is the best score you can get. I mean, to me, it's unprecedented. you know, because they feel it's an experiment, but they're excited about it, and based on the publications and what they're doing, it's, you know, it's like I say, it's the finest score I've ever seen in my career. Well, I couldn't do better, but
No.
It
will be.
Yeah, but so to me, I think we're all very proud that it you know, is getting, you know, that kind of score.
Yeah, yeah. So there you're purposefully mixing different disciplines, putting these groups together, and you've done that in your own lab, regardless of what building it's in.
That's correct.
Yeah. So so proximity matters.
Yeah. I think that's really a great point. I think proximity, I found that my whole life. You know, when I worked in Children's Hospital as a postdoc, you know, sometimes it's like even riding up the elevator with somebody, you know, and you're talking to them and you come up with ideas. I can remember an example of that with a cardiologist, Bob Levy, and I think for our students, like it gets me happy. You know, they're at some pizza thing or beer thing, and I think proximity really does matter. You know, there's that you end up. When I think about it, a lot of people I've ended up writing papers with and collaborating with, particularly clinicians, you know, they're actually very close friends of mine. Like Nick mentioned quite a few of them in the introduction. I met them when I was postdocs, and they've been friends of mine, close friends, for 30, 40 years.
Yeah, yeah. So just having those close connections, people you can talk to, sharing ideas, all of that.
Yeah, but also, you know, you're a close friend. You know, sometimes it might not happen because you're trying. You know, it could be a social thing because you're their friend also. Right.
Yeah. Yeah. Good. So so you're not part of a med school, but you've got some close by.
Yes.
Have you? You know, when you listed frustrations, they were, you know, turnover in companies and regulatory hurdles.
Right.
What about the frustrations on that happen in the translation-related? You didn't list, you know, not being part of a medical school or having to negotiate partnerships on the clinical research and clinical trials and all that. So you're happy that stuff works itself out pretty well?
Well, I think so. The question, I think, was aimed at the companies themselves. You know, I think all these things, sometimes the things that you're saying could be part of the companies, they could also be before the companies. And I don't know that they always work themselves out so well. I do think those are issues. I suppose over the years, you know, we've learned ways to navigate them. And, you know, and like I say, we are lucky that we, A, have the companies and B, have those hospitals near. But no, those can all be issues too. In other words, trying to move things forward, I mean, that's a challenge. And it's a challenge every step of the way.
So we heard two examples earlier of individual patients that you had treated miraculously. But how do you...
I didn't do it myself, but yes.
That's exactly my question. How did you have access to patients as a chemical engineer at MIT?
Well, I didn't, but it goes back to what we were saying, is like I collaborated, like Nick mentioned, like Jay Vacanti, he's my close friend, and he was head of pediatric surgery at Mass General, so he, you know, we'd collaborate and he would treat them. Or Henry Brem is chief of neurosurgery now at Johns Hopkins, and he's a collaborator, and he would treat them, for example.
So he would ask you for a device or a chemical and apply it to his patient?
Well, they're two different things. In one case, with Jay, the answer to that would be yes, because that was a specific patient. With Henry, what happened is we got a grant from a company that licensed our patents, and we worked with the company and developed what's called this gliadel wafer that Nick mentioned, you know, and that took many years. But he was the initial clinical, he did the preclinical work, and then he was one of the 5 main hospitals that did the clinical work. So when the first Lancet paper came out on the clinical trials, you know, he was first author on that, and he, you know, he's continued to pioneer that procedure to this day. You know, the idea of little wafers that you can put in the brain to deliver drugs for, you know, for different for brain cancer or other things. But so they're different. But I mean, I don't treat patients. I have, like I say, clinicians in the lab and then clinicians who I collaborate with.
So how do you fight these silos? How do you encourage people across the silos to start working together? Are there particular techniques? Well, one of them is put them in the same building.
I think that's, yeah. Well, one of them's put them in the same building. Another, to me, is money. I mean, you know, I think one of the ways that they did it at MIT, and actually I'm on the board of trustees at Cornell, is you have grants that say we will only get, I'll make this up, but it's not far from, let's say we'll give 5 grants for $500,000 apiece, but the requirement is that you have to have co-PIs. It has to be a collaboration between, say, a clinician at a hospital and a scientist or engineer at a university. And when there's money, people write grants because faculty want money. And that
Excellent
really
motivator.
And that fosters that. So one way is what you said, is you put them in the same building. Another way is you have some type of grant competition. Both those things are good, and they're hardly exclusive. I mean, the more ways you come up with those kinds of things, in my opinion, the better.
So let's talk about training. So I was in the Harvard MIT Health Sciences and Technology program. So I spent a year over at MIT during my med school years, and that was really useful actually to see both sides of the river, and how the engineers approached problems and how we approached problems and all that. It was very useful to me. So what about education? How should we be? For me, that was important and opened my eyes up into different ways of approaching problems.
Yeah.
Should we be thinking about that as we build our curriculum?
Yeah, I think so. I mean, I think that's a great program. I remember being on the admissions committee of it for a number of years. And
were you on it when I was?
I think so.
Yeah.
but you did fine.
Yeah.
So, but I was on it for a number of years, and but I'm still very involved in the program, and I think it's a great program, and I do think that kind of thing it's basically trying to teach. The way I sometimes think about it is it's just much more scientifically oriented or engineering oriented than a regular medical school program, even though you learn the medical school things, and sometimes it's more research oriented too. But I think that kind of program does train a different breed of, I mean, you would know better because you lived through it, but I think it does train a different breed of clinician, and I think that it's a good thing. I mean, I think that the people who have come out of that program, in my opinion, have done spectacularly well. I mean, they've, so I think that it attracts very good people, and I think it's trained people to, think somewhat differently because of that training. So I'd be very positive about it myself. I mean, like I say, you could be a better judge than I because you lived it.
Well, it was great to open your eyes up to different ways of approaching problems, more pragmatic approaches, breaking down problems to solvable components, that sort of thing, and just exposure to that whole world.
Right.
Could you say a few words about what this program is? Is it an MD-PhD or?
It can be. For me, it wasn't. It was a 4-year program for me, but many of the students do MD-PhDs, and they can get their PhD at Harvard or MIT. Most choose MIT for it, even though those PhDs take 7 to 9 years. It's an outrageously long time to add to a 4-year medical school, which is partly why I did my PhD later and at Berkeley, actually.
I see.
But they take the basic sciences, so those first 2 years, and instead of being in with the other Harvard students, they're primarily at MIT. There's some of the classes that happen at Harvard, and many of them happen at MIT. And they're taught by mostly MD engineers, people who have engineering backgrounds as well. And they take that sort of more, that approach that you'd expect engineers to take to medical problems. It has actually been a very successful program. In terms of what people have gone on to do. Much more research-oriented, but a lot, too, working in, in companies and starting companies.
Which Harvard? Is this Harvard Medical School?
Medical school.
Yes.
Yeah. But nothing about entrepreneurship, nothing about, what makes a successful health product, none of that.
Right.
So how important is that, and at what stage of training?
Well, I think the entrepreneurship's at a different dimension, but I think it could be useful at any stage of training. It's kind of what I maybe was saying earlier. It's like, I think that first, I don't think everybody should necessarily be an entrepreneur. I don't think that people should do what they want. But I think it's an option that is good to make available to students if they do want it. And I think I've seen it happen at the undergraduate level. I mean, obviously both MIT and Stanford do it. I've seen it happen at the graduate level, and I think, you know, different places have done it different ways. Like Stanford, for example, has this like biodesign program. I also think very highly of that. You know, so that's a way to try to bring it in. MIT, even if it's not directly, even if you don't bring it in directly to the HST program, you know, they still have things like the 100K competition, and I know, you know, a number of people in HST actually have competed in that and actually won. They have things like this Lemelson Prize for inventors. They have, so they, and I've seen number of HST people win. So I think that, so I think it's there if people want it, and they can choose, you know. So I think having options and having the exposure if they want it, I think that's a good thing. But I don't want to, I wouldn't necessarily make it a requirement or anything like that. I wouldn't make it a requirement. I mean, it just should be there if that's something that people want to see. But if somebody wants to go and do great basic biomedical research, that's good. If somebody wants to become a wonderful clinician in the country, I mean, that's good too. And it doesn't, in other words, there's all kinds of wonderful careers, and I think you just want to give people the opportunity to pick something that's in their heart.
So going back to HST, couldn't we here in Austin do our own version of HST?
Yeah.
We have a medical school, we have an engineering school. Can't we do it wouldn't be called HST, but you know.
It should not be called HST for sure. Well, we could. So the way we've thought about, so
you could
so
totally
far,
do TSH or something with Texas, you know.
Yeah, TSH.
Good
I don't
idea.
really like that, but we'll come up.
We'll
with something.
figure it out.
The we will. I mean, this is. I want you to do most of the time, but I'll just quickly tell you about how our curriculum works. So we squeeze in what used to be this horrific 2 years of facts that now is easier to get off your cell phone and using Google than it is trying to cram it into your brain. So we squeeze that now into a year. And then in the second year, they go out into the clinics. Usually that was in the third year. So they do all their core rotations, learn what it's like to be a doctor. In the third year, we do a year called, it's for innovation and leadership. And it has tracks in it. One's a research track. And that a lot of things can be done in that. I can get back to that in just a second. Another's related to population health, and another is healthcare redesign. That's a full 9 months, actually, that we set aside in that third year. And then the fourth year, they go back and they do their clinical subspecialties and other electives. One of the options during that research year is to actually get a dual degree. And the degree that we've been working on with engineering is Master of Science in Engineering. So that would provide a kind of a freer way in which to explore engineering and its principles. It's got to be project-based, though, too. So we actually have them working on real projects during that time. So I think that will allow them to select out a path for a subset of them that have a particular interest in this space.
Yeah, no, that sounds good.
Yeah. I'd like to do it later in the training as well. So that's the medical students. But actually, as you get more mature in your training, you actually are more useful. And I'm sure you found this in your lab.
Absolutely.
Yeah, so the medical students are not actually very knowledgeable. That's why they're in medical school. But when you get them after, like as fellows or as senior residents, they're a totally different breed.
Right.
And when do they come to you?
Well, I've had them come at all stages, though the fellows was what I was thinking about when you were asking me earlier. But I've had people do MDPhDs. I've had people in that HST program who just do an HST thesis. And then MIT and Harvard also have this other thing called the MEMP program, Medical Engineering, Medical Physics, where it's actually more getting a degree in an engineering discipline, but then taking a number of courses, medical courses in the HST program. So I've had students in all those, and they've all been outstanding, which is great. But I think what you said is right. I mean, the ones that have been most helpful in terms of changing the perspective of the lab have been those that were fellows, because they are more advanced and they really understand the problems, so they end up contributing in all three of those ways that you mentioned earlier.
Mm-hmm. Yep, good.
And they have a real perspective because they've seen a lot.
Yeah. So we're a brand new medical school, completely starting from the ground up. And obviously we've made some decisions already, but actually I've been here just a year, and there were just sort of 2 employees for the medical school for a number of months. So not much has happened yet. Let's say you're in my place. You're creating this new medical school. Mm-hmm. How should we do it to optimize the impact on society? So you seem to share that. You do it through health products. We will too. That won't be the sole way in which we impact society. Obviously, we have a strong community health bent as well, looking at population health. We have actual clinical care. But health products is going to be critical to our success. So how should we be designed?
Well, what I'm going to say may be oversimplistic. I'd probably go through a process. But I guess what I'd try to do is figure out, to the best that you can, if you start to project the next 30 or 40 years, what areas of medicine are going to be absolutely the most important, at a high level, and make the greatest impact. And, maybe I try to have some blue ribbon committee of clinicians, scientists help figure, and others figure that out, and, and sort of prioritize those. And then I would try to get, and this again is overly simplistic, but I would spend whatever money you need to get absolutely the very biggest superstars in those areas here. And steal them from anywhere, give them what they want, and build around them. But that's how I would think about it.
Welcome to Texas.
I'm not a clinician though, so you want to have.
We're not limited to clinicians.
No.
We want to cohabitate people with different perspectives.
No. By the way, I think that's good too, but I do feel still I do feel that's good too. But I still feel at the heart of it, that it is a medical school. So you really, the most important thing is to have, the very, very best clinicians. But I totally support having I think thinking out of the box and getting bioengineers involved early, that would be very smart.
Yeah.
But there have to be in your mind or other people's minds certain, medical areas that you just feel, whether it's genetic medicine or other kind, that I'm sure you've thought about from what you've seen, and, probably get advice, where can you push the field of medical practice? Even in bioengineering, there's probably things with new forms of surgery and stuff like that. So thinking about where the future will go, that seems to me, and having, clinicians who can really drive that. But I think taking advantage of this university and its bioengineering department and other things, that would be a very smart thing to do.
Yeah, no, there's so many strengths across the university. Engineering is particularly strong. Natural sciences really strong. It's all over the university. So, and we definitely don't want to reproduce what is already strong here. But you're right. What we want to do is pull in on the medical side, on the connections. That
and that's really what I meant. But I think that that's a wonderful opportunity. It's also a big challenge.
So here we have a blue ribbon panel of 2. So what are those areas, do you think? I don't want to give you mine, but
Well, I think some that come up that I think about, but again, I'm doing it more from an engineering perspective. I do think, different types of things with genetics, or gene type of therapies of different sorts. I mentioned mRNA before, but DNA, CRISPR, things like that. But the question is, what's going to be the next area of those? And I think hiring, some, really top molecular biology type people would be great. I think another area that crosses across different types of things in engineering and medicine is this whole bioinformatics, collecting, new sensors, collecting lots of information, understanding how you could predict disease and things like that. I think that to me also is another, big area. But, I expect there's going to be new kinds of things with surgery, like I mentioned, whether it's robotic surgeries or, remote control surgery into the third. I could think of different kinds of things that one might do. And I haven't done an analysis of, nor would I be the best person to figure out where you could have the greatest impact. But those would be a few that come to my mind.
And, I was thinking about the answers to that question. Of course, the answers then are a list of everything that's wrong with me. So I want those things fixed. So Travis County, we should lower the BMI.
You have the full hair, so you don't need that product.
No, but BMI. So Travis County has a BMI problem.
Yes.
So let's lock 10 or 15 points off that. How can we do that?
Yeah.
That's up there. Since obesity causes almost every other disease.
Yeah, no, it's a major, major
Sure.
public health problem. Not just Travis County, obviously. Good. Well, so what you said we should do, Blue Ribbon Panel, come in, figure out those areas. Well, you don't do that when you define your next area of major study.
No, I don't. I could, but I use a smaller Blue Ribbon Panel, the people in my, my friends and the people in the lab.
Right.
But I think it's different. In other words, it's one thing to try to identify a simple research problem or a research problem you want to solve. See, I don't.
That's a whole big area.
Yeah, I wouldn't want to be presumptuous about. I don't. To me, it's a much higher level question that you're asking than that I'm asking.
Yeah.
And because really, my experience is that what you want to do is pick broad areas which could have huge impact, and then just have a superstar people, go after them. And I think if you create the right environment with the right people, it's going to be very hard to say that they're going to solve even any of the things that I just said before, but they'll do well. They'll solve some big things, and they'll make you all proud.
Yeah, yeah.
And that's what I was looking for.
Good. So in programs, so you've probably seen a lot of programs asked to review all sorts of programs. So what's common to successful programs? Or give us an example of one that you think is particularly successful.
Well, it's great people. I mean, I think I'll pick MIT. This is more a basic science thing, but so I'm on the board of directors of MIT's Whitehead Institute, which you're probably saying, I think that's a great institute. I mean, they have, I think, more than half the people in it are in the National Academy of Sciences. I think they have 3 people who've received the National Medal of Science. There's only 20 faculty members in it, if that. I think that that to me, and they've done important things, like that's been one of the major places for genome sequencing. That's been one of the places where they've done a lot of the pioneering stem cell work. I mean, it's basic work, but it's basic work that's led to, very, very important things, I think, for the world.
Mm-hmm. And how about institutional programs that try to create the teams or provide mechanisms for seed funding? Examples there of programs that you've seen that are successful?
So mechanisms that create a team, I'm not sure. Seed funding, I can.
Yeah. So, well, one of the issues that we had at UCSF is we had all this fabulous basic science going on, and then we had clinical research kind of disconnected from that basic science. And somebody asked a question over there about how do you convince people that writing the paper isn't the end game? And so, because that is definitely a big part of the culture of these large research-based organizations like UCSF. And so, our part of our job was to figure out how to then get these things out so they could actually help people.
Right.
And so we created programs to try to do that, to bring teams together, to use seed funding, to get advice from folks outside of academia who really understood what a health product should look like and what the next step should be. So I'm just curious about programs like that. You didn't require these programs, but many institutions aren't as thoughtful about taking these steps as MIT is.
Yeah, well, I think like I said, I think Stanford's biodesign program, that's a good example, I think, of.
Why don't you describe that, because probably most of the audience.
Well, as I understand it, and you may understand it better than I, but I remember when I was out at Stanford giving a lecture, Paul Yock and others, they have this program, and it would often be clinicians working together with business people and sometimes others to solve a problem. Like somebody would dream up, I'll give an example. He said, well, could you come up with a form of surgery where you wouldn't have a scar? Could you come up with surgical instruments? And so they try to figure something like that out, and that could lead to a company. It would certainly lead to something that a lot of people would want. And I think when I talk to the clinicians and to the scientists and business people, I mean, it really seemed to be a very good program. I mean, he just, ended up writing a book, looking at various case studies on it, which I also felt was useful. But I mean, it's really creating a somewhat structured and yet still pretty broad-based program to get people with very different disciplines together to solve a problem that's of real importance or value to human health.
Mm-hmm.
I just picked up, there's the medical school, there's the UT Austin that existed prior to the medical school, but then there are these hospitals. Those are also involved. So Seton is our partner there?
Well, Seton's our primary partner on the inpatient side. And we hope to develop, to be more even-handed in the way we deal with community hospitals. But currently, Seton's our primary partner.
So would the relationships with, say, engineering and scientists on campus be with clinicians at those hospitals?
Well, so there are clinicians at that hospital that'll be our faculty. Our faculty will be in those hospitals. The ones that we hire will place there. And then there are clinicians at those hospitals that won't be our faculty. We take on our charge as being about elevating the practice of the entire community of physicians, whether they're our faculty or not. But we know that our faculty will tend to be much more interested in what's going on the research side and more entrepreneurial, and they'll be invested in education.
So are there any analogies between, you have relationships with hospitals that are not part of MIT. Mm-hmm. So this, analogously, these are hospitals that are not part of UT.
Right.
So what structures are there for getting engineers and scientists connected to these hospitals? How does that work?
Yeah, I mean, there's not really terrific structures. I think what happens is sometimes people would talk to each other, and it might happen kind of naturally. There have been times at MIT when they did have this kind of grant structure. The Whitaker Foundation once had a grant structure where they would do what I suggested before, that people could have joint grants if they were, say, at MIT on the one hand and one of these hospitals at the other. So there are things that could be done.
So joint grants comes up again as a...
Well, like I say, money gets people together because people want grants. I do think that things that I've seen work best are the proximity issue that you raised before. I still think that's the most useful. But then I think money fuels a lot of these things, and I think that's also very useful. Mm-hmm. And it's not, even if you don't get it, it's like just the process of people competing and collaborating to write the grant and think about it, can lead to things.
I didn't realize that we had spent, we meant to save 10 or 15 minutes for the audience to ask questions, and I just looked at my phone, and there's only 5 minutes left. So yeah, let's. Can we open it up? Questions from the audience? Tom.
Well, I mean, there has to be something that initiates it. I mean, MIT, for example, like I mentioned, has this 100K competition. This is at a younger level. It's students but they have a business school, a Sloan school, and they have scientists. And, what they do is they compete. I mean, they will have the types of people that you mentioned working together to sort of put together a business plan and then present it in front of people. And I think that's led to quite a few things at MIT. So I think having some type of structure or competition is one way to do that.
Have you ever gotten a Deshpande grant?
Yeah, a number of years ago, and I'm on the board of that at MIT, and that's the second thing. I was thinking, I wasn't sure how many to mention, but having these are grants that could give you anywhere from $50,000 to $250,000 to sort of bridge the gap from, certain type of early stage research to maybe getting something done that will help you start a company. And that can be helpful too, and they sometimes bring in outside kind of business mentors to help the scientists on things.
Has there ever been collaboration, not about medical schools, but with schools of nursing in either of the areas of innovation?
I have not seen that in the Harvard MIT thing, but there certainly could be. I mean, I don't think there'd be anything. I mean, I think people would be happy to do so, but I have not seen it. I don't know about yourself.
Yeah, well, it's not at Harvard, but there's no nursing school at Harvard, so that's not a good place to look for it. At UCSF, there were ties between the nursing school and the School of Engineering, but it was in Berkeley. It's much easier to bring those together here, and I think it's a great idea. I don't think it should be limited at all to medicine, whether it's nursing or pharmacy or any other area where you've got a distinct perspective. Particularly with digital health, a lot of those are focused on issues that nurses know best, actually. So hopefully we'll see the nursing school take a lead in that.
May I ask another question?
Yes.
Thank you. You've been in business a long time running research projects, and you developed a concept, and you started proceeding down the road, and you recognized there's a weakness in your team. And I would guess that starting a hospital, that's going to be one of the important questions. You've got to recognize if you got balance or you don't have balance. So what do you do in this condition?
Well, if there's a weakness, I mean, try to plug it, by getting the right kind of postdoc or to help it. I mean, for me, that's what we've done. I mean, if there's an area of expertise that we know we need, then usually we're able to get it, through having the right kind of postdoctoral fellow. It's a sort of soft money thing for a couple of years, but that's generally what we've done.
Nicholas?
I have a slightly difficult question. You held the position at Harvard. I don't know if you still have it. You were not paid your salary from Harvard Medical School, but you had the position. You have definitely former postdocs and graduate students, Marcia Moses, Aliko Phsensitive, many others, Omid, who are paid from the Harvard payroll. And the medical school payrolls are a little bit different than what we are used in engineering and life sciences.
You mean they're higher? You mean they're higher?
But a lot softer, a lot more soft money, yeah.
On NIH funding and similar funding.
Yep.
Where a large percentage of the salaries, not all of it, has to come from.
Much is your point, yeah.
Yeah.
And you hear what's happening in NIH, perhaps you are starting hearing like all of us do. There's going to be a limit in the number of grants. And frankly, when it first came out a year and a half ago, many of us thought of Harvard and Boston and a few other areas. UCSF. This system cannot change. If it changes, it's going to ruin the medical schools. Do you have any comments about whether NIH or the government is ever going to employ where they will say, limited the number of grants, you not pay 100% of your salary?
Well, they may. I don't think that's a good idea. I mean, I don't like that idea. I mean, to me, I think you do want to fund excellence. I think you want to fund the very best grants that can have the biggest impact. And so if people are doing important work, I'd want to see it funded. There's a number of things embedded in your question, but that part of it, I feel you always just, I believe in doing things that are merit-based and science-based. I'm not sure if you...
Yeah, no, I think that I agree. So maybe last question? Yep.
I'm not sure. You're probably better able to answer that. I mean, no, I mean, because
Well,
I think the
there are a
HST,
lot of
I think,
pieces there.
yeah, there
Yeah.
are a lot of pieces. And I do feel like the program that you went through, I mean, the HST program is a good example of enabling somebody to do that. That may not be exactly what you were asking, but I think that program is
Well, the way you answered it, too, when we talked about entrepreneurship, I think is good. That we can't, medical school is already impossible in 4 years. And we're trimming it in every way we can to make it feasible in 4 years, introducing a whole new skill set to students in that innovation and leadership block. But we have to allow the students to differentiate as well, right? So we can't teach entrepreneurship to every student, just as you said. And some are going to be more community focused and interested in global health. Some are really going to be fascinated by surgery and want the engineering principles. Some will be drawn to the lab, and we want to support that. It's giving the ones that will need the skill set that you described, that skill set. So I think we have enough flexibility to do that and enough connections with the other schools to give them the kind of vocabulary and underpinnings to be able to talk cross-discipline when they need to. But I think the other part of your question that was particularly intriguing was you said continuing medical education. So I don't think we can force medical students to differentiate accurately at that early stage. And I think what we have to do is start to push that training out into their residencies, into their fellowship years, and then even after they're out in clinical practice. It is one of the great things about academic medicine is it broadens your scope. One of the hard things about clinical medicine in isolation is that after a while you get really good, and getting good means it's less stimulating to you. So there is a point too where people are in practice where re-engaging them and broadening their scope could be really interesting. So we're thinking a lot about continuing medical education. Actually, not in this area. So your question's really very interesting. Do we have a cadre of clinicians out there that really want to start thinking more entrepreneurially around health products? So that's a great point. I think we can talk about floating some ideas for continuing medical education and see where they go. Great. I think.
All right. Well, please join me in thanking Dr. Langer and Dean Johnston.